Gravitational Fields worksheet, starting from question 2, where we are told that on the surface of the moon, if we have a 20 kilogram mass, it will experience a force of 32 newtons. So clearly here, 20 kilograms, 32 newton force. What force is acting per kilogram? The gravitational field strength, remember F equals mg. So the gravitational field strength, which is just the force acting per unit mass, will be 32 newtons over 20 kilograms, which is 1.6 newtons per kilogram. What we're then told, okay, is what force is going to act on a 70 kilogram mass, on an astronaut of 70 kilograms. Well, if we've got 1.6 newton acting per kilogram, the force acting on that astronaut is simply going to be the mass of the astronaut, which is 70 kilograms, multiplied by the gravitational field strength of the moon, which we've already established using the smaller mass, is at 1.6 newtons per kilogram, and we will get the force of 112 newtons. And so that is the answer to question 2. 3. What we have in question 3 is we've got the Earth. There, let's label that. And we've got a satellite in a low Earth orbit above the surface of the Earth, and we are told that the radius of that orbit, or the distance it is above the surface of the Earth, is 800 kilometers. We're asked to work out the gravitational field strength in the region of the satellite, and so we know a formula for that. It is gm over r squared. So we can put numbers in here. Big G, the universal gravitational constant, is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. The mass of the Earth, now we need to look that up. We're not given it in the question. It is on the front of our data sheet. If you look at the bottom left of your front page of your data sheet, the mass of the Earth is 5.97 times 10 to the power 24 kilograms. And we need to divide that then by the distance. Now the distance here needs to be measured from the center of the mass of these bodies. So from the center of the Earth to the center of the satellite. So what we need to do here is we need to add on the radius of the Earth, because the 800 kilometers is the distance above the Earth's surface, but we've also got here the radius of the Earth. Now again, we can look that up on the data book. The radius of the Earth is 6.36 times 10 to the power 6 meters, plus then we've got to add on the distance the satellite is above the surface of the Earth, which is 800 kilometers, so 800 times 10 to the 3. And don't forget, on the bottom here, the distance must be squared. These are an inverse square law, so we're squaring the distance. And if we work out all of that, we will get 7.75 newtons per kilogram. And there is our answer. Question 4 says gravitational field strength based on inverse square law. What is an inverse square law? Well, simply here that the gravitational field strength is proportional to 1 over r squared. And that's called an inverse square law. And what it means basically is every time we double the distance, 1 over 2 squared is a quarter. So doubling the distance will produce a quarter of the gravitational field strength. Triple the distance, well, 1 over 3 squared will be 9th, and we'll get a 9th of the field strength. So that's obeying there an inverse square law. Now question 5 asks about this situation. We've basically got a 300 gram mass, label that there, and we've got a 500 gram mass. And what we're going to do, well, those two masses are 40 centimeters apart. We're going to place a smaller mass, a 75 gram mass, at their midpoint. So if measured from the center of gravities here, what we've got is that distance there is going to be 20 centimeters, or 0.2 of a meter. And this distance here is also going to be 0.2 of a meter. Could we work out the force experienced by the 75 gram mass then in this gravitational field? So what we've got to realise is that this 75 gram mass is going to be attracted towards the 500 gram one and also attracted towards the 300 gram mass. So it's being pulled gravitationally towards this mass by its gravitational field and also towards this mass. So the resultant force here is going to be the resultant of these two forces. So what we need to do first of all, let's work out the force exerted by the 500 gram mass on the 75 gram. We just apply Newton's law of gravitation, G m1 m2 over r squared. Big G, gravitational constant, is always 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. We need to then multiply that. Now of course we need to change our masses into kilograms, so if we're looking at the force between these two masses, we've got 0.5 kilograms multiplied by 0.075 kilograms, and of course then that's all going to be over the distance squared, 0.20, and that is squared, and that gives us a force on the 75 gram mass applied by the 500 gram mass. It will give us a force which is 6.25 times 10 to the minus 11 newtons when you work that out. What we will then need to do is to work out, so if you like we can call that F1. We then need to work out F2, the force between the 75 gram and the 300 gram mass. What's that going to be? Similar calculation, 6.67 times 10 to the minus 11, but this time we've got a 0.3 kilogram mass multiplying our 0.075 kilogram mass. Divide that. Again, they are 0.2 meters apart, and we will get 3.75 times 10 to the minus 11 newtons. So that would be there F1, that would be F2. So the resultant force on the 75 gram one is going to be, well, because these are in opposite directions, it's going to be the larger force there minus the smaller one. If the forces are in opposite directions, the resultant is just found by taking the smaller force from the larger one. So resultant force here will simply be 6.25 times 10 to the minus 11 minus 3.75 times 10 to the minus 11 newtons, which will give us 2.5 times 10 to the minus 11 newtons, and that is the resultant force. And really, because force is a vector quantity, we should give a direction. So that is towards the 500 gram mass. And there we are. Okay, in question 6 we are asked about Mars, and the first thing it says is write a word equation that states Newton's law of gravitation. So Newton's law of gravitation, basically force equals gravitational constant multiplied by mass 1 times mass 2 divided by distance between centre of mass squared. So there's our word equation. What we now need to do then for Mars, we're told that the mass of Mars is 6.42 times 10 to the 23 kilograms. We're told the radius of Mars is 3.4 times 10 to the 6 meters. We are asked to work out the force acting on a 1 kilogram mass at the Earth's surface. Easy. Gravitational constant, 6.67 times 10 to the minus 11. Put in the mass of the Earth, the mass of Mars, 6.42 times 10 to the 23. We've got a 1 kilogram mass then at the surface, which means the distance away from the centre of Mars of that object will be the same as the radius of Mars, which is 3.40 times 10 to the 6 meters. We must square that, and if we work out then the force, we will get an answer which is 3.70 newtons. So basically the gravitational field strength at the surface of Mars is 3.7 newtons per kilogram. 7 here. It says the gravitational field close to the Earth's surface is often described as uniform. With the aid of a diagram, what is meant by a uniform gravitational field? Well, a uniform gravitational field is one where the gravitational field strength is constant. As you move through the field. And what that means is that the gravitational field lines will be parallel and equally spaced. So if we've got a uniform field here at the surface of an object, if we draw the gravitational field lines at the surface of the Earth, the gravitational field lines across a small region of the Earth's surface will be basically parallel and equally spaced. There would be the field lines. So if we just look at across a small section of the Earth's surface, what we would have is that the gravitational field lines are parallel and equally spaced. Remember, the separation of the field lines indicates the strength of the field. The closer the field lines get together, the stronger the field will be. The further apart the field lines, the weaker the field. It then says we've got a diagram. Yes, we've got a diagram that looks a bit like this. We've got the Earth here. We've got the Moon over here somewhere. And what we've got is a spacecraft moving across basically from the Earth towards the Moon. As the rocket moves further away from the Earth into the region BC, so that's this region here. As the rocket moves further into the region BC, why is it that the decrease in kinetic energy of the rocket per kilometre of path gets less? Explain this. So really it's simply the fact that the gravitational field strength of the Earth is getting weaker. Okay, so basically from B to C, gravitational field strength decreases. So the gravitational force acting on the satellite or acting on the rocket, really I should put acting on the rocket back towards the Earth decreases. We know, of course, work done is force times distance. So for every kilometre it moves, if there's less gravitational force acting, because we've moved further away from the Earth, the work done against gravity is going to be less. So here, smaller force means less work done. Against that gravitational force per kilometre. And there we are. Okay, so from B to C, gravitational field strength is decreasing. The gravitational force then acting on the rocket back towards the Earth is decreasing. We know that work equals force times distance. A smaller force, smaller gravitational force, means we're doing less work against gravity, and that basically there is the answer to the question. Okay, so the decrease in its kinetic energy per kilometre is going to get less because you're converting less kinetic energy to gravitational potential energy. We're looking at this rocket here, moving from B to C. We're told that by the time the rocket is at D, over here somewhere in this position, so by the time it's moved all the way across to here, we're told that at that point the resultant force is 0. So when we get our rocket here in this position, the force pulling it towards the moon is the same as the force pulling it towards the Earth. So we can actually equate the gravitational forces here. Basically, the gravitational pull of the Earth will equal the gravitational pull of the moon on this rocket. So we can say here, we know from Newton's law of gravitation, gravitational force is G times big M, which would be the mass of the Earth, multiplied by the mass of the rocket, I call that mr, mass of the rocket, divided by, now we're told the distance from the centre of the Earth to point D is 346 times 10 to the 3 kilometres, so 346 times 10 to the 6 metres then. Of course that's squared. If we look at the moon here, the gravitational pull of the moon is going to be big G times the mass of the moon times the mass of the rocket, and the distance from point D to the centre of the moon, we're told that's 38 times 10 to the 3 kilometres, so 38 times 10 to the 6 metres, and again don't forget that that is squared. Now we can do some cancellation once we've equated those. Obviously big G, the gravitational constant there, occurring on both sides, so we just cancel that out. The mass of the rocket, well that's going to cancel out as well. So we can rearrange this equation to say, look, mass of Earth over mass of Moon, so just dividing through both sides by the mass of the Moon, and then multiplying both sides by 346 times 10 to the 6 squared. What we're going to find is a ratio here for the mass of the Earth over the mass of the Moon, which is what we're asked to work out. And if we work that out, that ratio comes to be 82.9. So basically the mass of the Earth is 83 times the mass of the Moon. And that's how we'd go about doing that in answer to question 7. Question 8 says we have two identical lead spheres. Each have got a mass of 6 kilograms and the density of lead is 11,400 kilogram per meter cubed. So basically here we've two identical lead spheres. So if there's our lead sphere, what we know is that it's got a mass of 6 kilograms and its density is 11,400 kilogram per meter cubed. The first thing we're asked to work out is the radius of this sphere. Well, what we know is that density is mass over volume. So we can easily get the density of the sphere just by doing its mass over its get the volume of the sphere by doing its mass divided by its density, just by rearranging the density formula. We know the mass, we know the density. And so if we work that out, we can get a value for the volume in meters cubed, and it's 5.6 times 10 to the minus 4 meters cubed. But we know that volume, if it's a spherical object, the volume of a sphere, which again is on the bottom of your datasheet, first page, bottom right, the volume of a sphere is given by 4/3 pi r cubed. So we can set that equal to 5.26 times 10 to the minus 4 meters cubed. So if we rearrange again, r is going to be multiplied by 3 divided by 4 pi, take the third root, so 5.26 times 10 to the minus 4 times 3 over 4 pi the third root of that. And if we do that, we come out with 0.050 meters. What we then have is we have two of these lead spheres which we are told are touching. So that was part A there. Part B, we've got two of these lead spheres, they're touching. So if they're both touching their centre of masses, imagine here two lead spheres touching, basically the centre of masses are going to be 0.05 times 2 meters apart. It's going to be 0.1 meters apart. So we can work out the gravitational force of attraction between them if they're just touching. Again, using Newton's law of gravitation. Basically, big G, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, multiplied by the mass of each object, so they're identical, they're both going to be 6 kilograms. And the distance apart, well, if they're just touching, the distance between their centre of masses will be the radius of one plus the radius of the other, so that's going to come to be 0.10 meters, and we're going to need to square that. It's got to be distance squared on the bottom, and if we work out that, we will get let's just work that out. And so we get 2.40 times 10 to the minus 7, and the unit there is newtons. Just squeeze that in at the bottom, and there we go. That's question 8. So in question 9, we're told that we've got the Earth. We're told that the mass of the Earth is 6 times 10 to the 24 kilograms. And its radius is 6,400 kilometers. We could have looked that up on our front page of our data book anyway, on the bottom left. And we're asked to show that the Earth's gravitational field can be considered to be uniform up to a height of 10 kilometers. So really all we've got to do is to show that the gravitational field strength 10 kilometers above the surface of the Earth is pretty much the same as it is at the Earth's surface. Now we know G is 9.81 Newton per kilogram at the Earth's surface, so let's work out what it is 10 kilometers above. We know gravitational field strength of the Earth or any object is given by G. G is the gravitational constant, Gm over r squared. We know that big G is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Again, we can look that up in our data book. We can look up the mass of the Earth, bottom left of our data book, first page, but we're given it in this question in any case. So that's 6.0, we're told to take it in this case as 6.0 times 10 to the 24 kilograms, or you can use 5.97 times 10 to the 24, that's on your data book. And then we need to divide that by the distance from the centre of the Earth. And now we're trying to calculate the gravitational field strength 10 kilometers above the surface. So the radius of the Earth we're told to take as 6,400 kilometers. That's 6,400 times 10 to the 3 meters. But then we're actually going 10 kilometers above the surface. So the total distance from the centre of the Earth to 10 kilometers above the surface, well, we can work that out. Don't forget, distance has to be squared. And then it is simply a question of putting that into our calculator. 9.7 newtons per kilogram. So basically, moving up 10,000 meters above the Earth's surface, over that distance, the gravitational field strength has gone from 9.8 newton per kilogram to 9.7 newton per kilogram. It's a very small change, so we can assume we can take it to be constant over that period, because although the Earth is a radial field, so if we draw the Earth, we know around here that the field strength is radial, so the field lines will diverge like this. So remember, whoops, trying that the wrong way around. So remember, two things the gravitational field lines are telling us here. They're telling the direction of the force that a mass would experience when placed into this gravitational field, but also the spacing of these field lines gives us an indication of the strength. The more closer they are together, the stronger the field. So you would think as radial fields, we move away from the surface, the field lines diverge, they get further apart, so the field decreases, the gravitational field strength drops, and it does. But 10 kilometers, bearing in mind the radius of the Earth here is 6,400 kilometers, 10 kilometers added on to that is such a small distance. You're not going very far above the surface. Over that very small distance, these field lines have hardly diverged at all. You're just going up there a very, very small distance. And so over that distance, there's no appreciable drop-off in the field strength. The field can be considered uniform up to 10 kilometers above the surface of the Earth. And there we go.